A system of congruences has a solution if the moduli are pairwise coprime. But what if they're not? Under certain conditions, there might still be a solution. So suppose our greatest common divisor of two moduli is d, where d is greater than 1. If there is a solution, in other words, if x is congruent to a1 mod n1 and congruent to a2 mod n2, then we know that the difference x minus a1 is some multiple of n1, and likewise x minus a2 is some multiple of n2. So if we subtract them, we find the difference is, and since the greatest common divisor of n1 and n2 is d, then d has to divide that difference. And this proves that if there is a solution, then d divides the difference of the congruence. Now, if d doesn't divide that difference, then x can't be a solution. And so we say that it is necessary that d divides the difference of the congruence. So, for example, we might try to find a solution. We note the greatest common divisor is 5, so if a solution exists, 5 has to divide 3 minus 2. But this isn't possible, so no solution exists. Now, it's important to understand that we might have a different problem. Again, our greatest common divisor is 5, so again, if a solution exists, 5 has to divide the difference. And it does, but that only says that a solution might exist, but there's no guarantee that it does. Remember, a necessary condition might be one of several. In order to win the lottery, it is necessary to buy a lottery ticket, but it's not enough. So, let's introduce an obligatory math joke. How many mathematicians does it take to screw in a light bulb? 1. They give it to 3 plumbers, thereby reducing it to the previous joke. This joke explains 2 things. First, why Netflix won't return my calls. And second, how mathematicians approach problems. The Chinese remainder theorem applies if the moduli are coprime. If the moduli aren't coprime, can we rewrite the congruences so they are? Maybe. So let's start with one congruence. Suppose x is congruent to 11 mod 30. And the question to ask is, what other congruences must x satisfy? So remember, definitions are the whole of mathematics. All else is commentary. Since x is congruent to 11 mod 30, then the difference is 30 times something. But we can factor 30 in a number of ways. So this also means that x minus 11 is 2 times something, so x is congruent to 11 mod 2. X minus 11 is also 3 times something, so x is congruent to 11 mod 3. And also, by generalizing our work, we can prove the following theorem. Suppose x is congruent to a mod n and d divides n. Then x is also congruent to a mod d. We can prove this as follows. Prove this theorem as a homework problem. So let's go back to the first case where we know that no solution exists. Well, we already did that, but let's solve it in a different way. So if x is congruent to 3 mod 10, then our theorem says that x is congruent to 3 mod 2, and also x is congruent to 3 mod 5. If x is congruent to 2 mod 15, then our theorem says that x is congruent to 2 mod 3 and 2 mod 5. But if x is congruent to 3 mod 5, then x can't be congruent to 2 mod 5. And so if we solve the first congruence, we can't solve the second. Now, let's see what happens in our other case. So again, 10. Since 10 is 2 times 5, we can rewrite this as x congruent to 3 mod 2 and x congruent to 3 mod 5. But since we're working mod 2, we never have to work with numbers larger than 2, so we can actually reduce this first congruence. For the other modulus, 15, well, that's 3 times 5, so we know that x is congruent to 8 mod 3, as well as congruent to 8 mod 5. And again, if we're working mod 3, we can always work with numbers smaller than 3, so this congruence reduces. And note that this gives us one congruence we've already found. Likewise, x congruent to 8 mod 5 can be reduced to. And because the moduli are now coprime, there's a guaranteed solution, and it works out that the least positive solution is. And we can verify that 23 is congruent to 3 mod 10 and also 8 mod 15, so x equals 23 solves the system of congruences. It appears we can solve the Chinese remainder theorem this way, but notice the direction of our statement. If x solves the congruences with non-coprime moduli, then it solves the congruences with coprime moduli. But what we actually found is something that solves the congruences with coprime moduli. Will it always solve the original congruence? Let's take a look at that next.